Yeah, I guess I should start now. I have some voice problem, but anyway, for online class, it may not be that much problem. Uh, for the last two or three or other around some three classes, we're just trying to find out the different possible methods of waste heat recovery. And there I have mentioned that we will try to explore a few sample technologies through which the waste heat recovery can be made feasible. Because the most important challenge of waste heat recovery is that we cannot implement any waste heat recovery retrofitted system if it is not economically feasible vis-a-vis the return of the benefit of the investment through the recovered waste heat. So the waste heat recovery has to be that much efficient so that the recovered heat will justify the savings in corresponding fuel to recover that investment and the operational cost of any waste heat recovery. That finance part, which is called the waste heat recovery economics, we'll later discuss. But right now, we are going to another device, which is also very innovative device for larger scale waste heat recovery, where the process may be even more efficient. Let's see. Now, the presentation. Enter screen. Yeah. So, this is another very innovative waste heat recovery. It can be used for waste heat recovery or it can be used for independent heating of air. So, this is called pebble gas heater. So, what do you mean by pebble gas heater? Is pebbles, you all of you know, that means small marble like stony material. Stony means little bit harder material, is generally called the pebbles. So we are using the pebbles for the heating purpose, or rather more efficient heating purpose of air. Now, what is the idea of this pebble bed heat exchange is something like this. Here, let us just initially preliminary discuss, then I may give a text also. You find out that there are two chambers, and in between two chambers, there is a connection line or rather connection cross section, which is connecting the upper chamber and the bottom chamber. Now, regarding the upper chamber, we have shown two burners. Actually, these burners are shown because the pebble bed is not only used for waste heat recovery, but also generally it is used for any air heating efficient process. So, in case of waste heat recovery, these burners may not be there. Instead of that, the burner means you are burning some fossil fuels, specifically gas or liquid, in this burners to heat the pebbles inside. So that can be done not by, instead of burners, you can use available hot flue gas too. Now see the situation. If the pebbles fill up this upper chamber and there is a heat source, either in the form of burner burning the fossil fuel or some flow of hot flue gas, hot waste flue gas, then the pebbles are heated. Then, as it is connected to the lower chamber, due to simple gravity, these pebbles, heated pebbles, will come down here in the bottom chamber. Now, in the bottom chamber, what is the configuration? We have some perforated space through which air can pass, but based on this pebble size, no pebble can come out through these passages. So, if you make a cold air flow by using blower or fan, then what it is expected, as the air doesn't have any other passage to flow through, the air will only pass through these pebbles. And these pebbles are already heated pebbles. That means at a higher temperature pebbles. Now, as the air passing through these perforations, either this side or this is basically a circular, three-dimensionally, it's a conical section, and there are very small holes through which the pebbles cannot come out, but gas can easily pass through. Now, as the pebbles are there, then effectively what you are getting, depending on the density of these pebbles, the air will try to find out the interstitial spaces. Just let me admit someone. Why they are so late? Anyway, huh. So the interstitial spaces are, I mean, the air is forced to pass through these interstitial spaces. Now, what happens? Any heat transfer process, we call it a transport process. Transport process means the amount of heat transfer will depend mostly on three important parameters. One is the temperature difference, second is the surface area, and third is the time of contact between the heat exchanging fluids. If you can provide more time, then obviously, effectively, you will get more heat transfer. Now, see, in this mechanism, what the additional benefit do you get? If the pebbles are, I mean, stacked up heavily, then what will be the situation? The air passage will be very much restricted. So, to make the air flow through these pebbles, you have to make the blower pressure to be higher. And in that case, the consumption of power for the airflow itself will increase. But no doubt, you will get better heat transfer in a sense as the air passes through this small holes and is forced to pass through the gap or the interstitial spaces between these pebbles. So, obviously, more packed is the bottom chamber, the air will have to have a longer path and more time of retention during the passage through these pebbles. So, you will have a effectively better heat transfer, and then finally it comes out of the as in the form of hot air out. That means you can never achieve this much heat extraction. That's the temperature of the air is significantly higher than the any I mean, I'm telling any other, but the simply if you could have made the hot gas passing through surrounding tubes and the cold air is passing through the tubes, then obviously effectively the heat transfer or this temperature of this hot air would have been much lower. But here, with the same hot gas source, the through this pebble bed heat exchanger, you can achieve much better heat extraction and corresponding temperature at the hot air outlet is significantly higher. There will be two difficulties that how we will manage and this pressure control connections, etc. I will discuss later. But at first, let's make a small discussions about the pebble bed heat exchange process, the basic principle. Okay. Ah, so just write down in pebble bed heat exchanger, in pebble bed heaters, pebble bed pebble gas heaters, in pebble gas heaters, whatever is given. In pebble gas heaters, small pebbles, small pebbles are filled up in the upper chamber where it is heated either by using burner and fuel, either by using burner and fuel, that means fuel in burner, or using any heated waste gas, or by using any heated waste gas. These heated pebbles are then transferred to the lower chamber. These heated pebbles are then transferred to the lower chamber. Through the connecting passage, through the connecting passage between the two chambers. Full stop. Cold air, cold air is passed through these heated pebbles, these heated pebbles using a blower or fan, using a blower or fan. Full stop. Depending on particle density of the pebbles, depending on particle density of the pebbles, efficiency of heat transfer, efficiency of heat transfer between these pebbles, between these pebbles and the air passing through these, and the air passing through these varies. Full stop. Higher the higher the density of pebbles, higher the density of pebbles, or density বললে একটু confusion হতে পারে. Higher the particle density means how many particles in a given volume. Okay, higher the particle density of pebbles, better is the contact of air passing through it, better is the contact of air passing through these, and also more is the duration of air, and more is the duration of air within the pebbles. Full stop. However, next sentence, however, the pressure drop of the air, the pressure drop of the air as it passes through the pebbles, as it passes through the pebbles, also increases with higher particle density, with higher particle density, causing more power required, causing more power required for the fan or blower. Okay, hence an optimized operation has to be decided based on particle density of pebbles. Then write down after the heat exchange, after the heat exchange, pebbles are transferred from the bottom of the lower chamber, from the bottom of the lower chamber using pebble elevators, using pebble elevator. These are basically some, carrying process of the pebbles in some buckets, and these buckets also rotate on some chains so that those pebbles will be again supplied to the upper chamber. Okay. Uh, Now I'm coming to the one thing you have understood, that why the heat transfer is better. That is because the air passing through these pebbles have less passage, means it will stay for longer period within the pebbles, number one, and number two is it will have a better contact with the pebbles. But the problem is the pressure drop of these flowing air through the pebbles will also increase. So corresponding blower or fan power required to make this air to flow through the pebbles will also increase. That is electrical power consumption. So to increase the heat transfer, if you have to have more electrical power consumption, then it may not be justified. So there is an optimum pebble particle density, not the pebble density, but the pebble particle density. That means how many particles are there in a given volume of the lower chamber. That has to be optimized. There are certain engineering principles, and we can do that. Now, now there are two issues, because here you can find out that any gas and solid flow is quite easy. Okay, rather sorry, but the solid flow is not that easy in a sense, because the connections between these two chambers, upper chamber and the lower chamber, here the particles, they are not necessarily supposed to flow at a very uniform flow rate. Very accurate uniform flow rate. More or less, we can maintain this flow rate, but some choking problems sometimes happen very frequently. So what has to be done during the operation? You cannot stop operation just because of choking at this connection point between the upper and the lower chamber. So what you have to do, you have to make some arrangement so that this choking has to be cleared during the operation itself. So there is a pressure control connections. So see just the structure. This upper chamber is only exposed to the lower chamber through this connection point. Now, if your pressure connection point, the one point is connected to this upper chamber and another point is connected to this lower chamber, then because here it is blocked with a plate, means no pressure. Here the pressure inside the upper chamber and the pressure in the lower chamber is different. Now, if there is any choking problem happens, then what is done? The pressure, these are actually connected to not to blower. What is the difference between air, blower, compressor is these, all these devices do the same thing, but the pressure ratio increases. Means for fan, almost there is no pressure rise because all of us use fan at home for just getting some cooling effect. So fan pressure rise is very low. One ratio is either 1 or 1.1 sort of thing. So you don't feel that pressure rise. But for blower, it's up to 4. That means for the inlet pressure, the outlet pressure may be 4 times than the inlet pressure. But if it is above 4, you need to employ a compressor. Now, this airflow in the bottom chamber, we generally use the blower because up to 4 pressure rise, that is good enough. And that means 4 times the atmospheric pressure. That is good enough to make this airflow. Otherwise, the consumption of power will be too high. So, a fan or blower is quite good for the lower part air supply. But in the pressure control connections, you need to employ a compressor, because here, whenever there is a choking problem, you have to create a high pressure here inside and a low pressure here at the bottom, so that due to the pressure difference, the any choking of this pebble will be forced to, come from the upper chamber to the lower chamber. So this forcing is done only occasionally by observing if there is any significant choking of the pebble flow from the upper chamber to the lower chamber. So just write down this in the text, next paragraph. Okay. Pressure control connections is used pressure control connection is used to clear any choking, choking, any choking of solid pebble flow, during operation. Full stop. The principle includes raising pressure at the upper chamber with a lower pressure in the lower chamber. The upper chamber pressure may be raised using a suitable compressor. Full stop. However, the compressor operates only if any choking happens. Full stop. Otherwise, pebbles flow due to gravity from the upper to the lower chamber. Okay. So the operational principle we have explained. Now only thing what is left is what should be the properties of the material that is suitable for the making the pebbles. Any input from the common sense?
It should have high heat transfer coefficient.
That is one. Then actually heat transfer coefficient, honestly speaking, it is a good attempt. From the class you have at least responded. The heat transfer coefficient will itself depend. So heat transfer coefficient is a synthetic term because total heat transfer divided by the surface area divided by the per unit temperature difference gives the heat transfer coefficient. So heat transfer coefficient is basically
happens due to the arrangement we can make. From that viewpoint, the heat transfer coefficient actually increases not due to the so-called, the pebble has got certain role, I will explain, but not only due to the pebbles, but also due to the pebble packing itself that we have discussed. That if the packing is better or higher, then obviously the air passage will be lasting, lasting duration or more duration, and simultaneously it will have a effectively more longer path that's effectively leading to the larger duration of stay within the pebbles. So effectively we'll get more heat transfer, and that will increase the overall heat transfer coefficient. But another thing you think about the situation, which is called the heat capacity. When you are heating the pebbles in the upper chamber, then obviously how much will be the temperature and the content of heat of these pebbles will depend on the property of the pebbles. Now, that property is basically, it depends on the specific heat multiplied by per unit mass is the, specific heat multiplied by the total mass is the heat capacity. That means if the specific, unless the specific heat of these pebbles are high, it cannot have a large heat content. Means for the same two things are very important. One is the temperature, another is the heat content. Your heat transfer will happen due to temperature difference. Unless you have a good temperature difference with the heat exchanging air and the pebbles, you will not have sufficient heat exchange. And simultaneously, during that heat exchange process, temperature will decrease simultaneously because it is rejecting heat. But unless it has got sufficient heat content, air cannot get it. So that depends on how much is the specific heat capacity of the pebbles is also important. And generally the surface texture means outside surface, how it is, that also affects the heat transfer characteristics or improving the heat transfer coefficient. And your answer is right in a sense that heat transfer coefficient has to be increased somehow. But the heat transfer coefficient itself will increase on if you can make it a favorable heat transfer condition. But the heat content, how much heat is within these pebbles, because if it doesn't have sufficient heat, when the temperature difference is coming to, rather tending to a small value, not the zero, but tending to a small value, then heat transfer will automatically stop. But before that, if it doesn't have significant amount of heat, it cannot transfer large amount of heat also. So just write down different, কি বলতে পারি, uh, specific properties are required for the pebbles for better heat transfer characteristics. Full stop. These pebbles must have good heat capacity and surface texture for higher heat transfer. Full stop. Also, the size and shape of the pebbles, have some effects on the heat transfer performance. Okay, so what are these things? As I'm repeatedly telling that I cannot go into more engineering in these issues, because we can design the design of this particular pebbles can be a good MTech project, because design of the entire system, because there are issues. The air air Reynolds number will be needed. I mean that heat transfer coefficient. Based on that, we need the Prandtl number, and there are certain correlations available. But those mathematics, I'm not, rather the relations, mathematical relations, I cannot use in this open elective class. But you can have a guess that how it can be designed, because initially you have to make a estimation how much heat at what temperature the hot flue gas is available. So based on that range of temperature, you have to decide how much is the total heat transfer you are expecting. And then obviously you have to decide what is the capacity or the total loading of the pebbles. Then you have to choose the material of the pebbles. Then you can make those pebbles the proper texture, means outside surface of the pebbles, as required for the better heat transfer. Then obviously you have to take care of this entire design process includes the smooth flow passage of these pebbles by the pressure control connections. And then the in operation also, you have to be very cautious of maintaining the pebble particle density loading at the bottom chamber, unless you can control that, because the pressure control connections, it can be done either way. Either you can use it for smooth flow from the upper chamber to the lower chamber, but if the lower connection is at a higher pressure, automatically the flow will be reduced or even can be stopped. So depending on that, the during operation, the pebble flow, which is the most important part relative to the airflow, has to be controlled by this pressure control connections. And obviously, the during operation close monitoring of this pebble gas heaters is very much important. Anyway, so as I'm just giving the conceptual operational part of in this open elective class, the design part, I'm just giving some sketchy idea. We have understood that the process of selection of the pebbles, number one, the airflow relative to the particle density, another issue, because the airflow itself consumes some electrical power. Then smooth flow, or rather controlling the flow from the upper chamber to the lower chamber, controlling of flow of pebbles is by this pressure control connections is another important issue. And then finally, the properties selections of the pebble material and the pebble surface texture are the important issues. But during design, some more other issues has to be considered, like cost and other issues that I'm not coming into discussion. But as an engineer, or going to be engineer, if you be in a farm where this pebble gas heaters manufacturing is their problem, then they generally have their data handbook based on that, because all engineerings are not necessarily always done in industry according to first principle. They, from their experience, they make some data handbook for the selection process. If this is the range of temperature, select these pebbles. So in the market also, you have to have the availability, because when we discuss in the class, we discuss the principle, but when you go to the actual industry, you have to find out those real life implementation, and there you have to find out which type of material is at all available at a feasible cost in proper supply chain. Supply chain is also important. You have decided certain pebble material, you have find out from the material list also this is possible and this material is exist in this other world, but that supply chain is not there. The material you have chosen is not available in our country, or nobody is doing business for that. So deciding proper supply chain is also another important issue. So in companies, what they do actually, because I started my career in industry, and I find out industry not necessarily always make the system design from the first principle the way we teach in the class. They originally did that from their long experience, but the industry, to make a business profit, they cannot depend on the employee, that every time very innovative employee will be there and they will do it. So they make it a data handbook. There the company person or engineers has to choose the proper things as per the data. If this is the temperature, select this one. Next step, if this is the selected pebble material, then go for the size. Then size also has got certain empirical relations depending on the airflow rate and temperature and etc. etc. So those empirical relations actually are decided from the experience of the operation. And empirical relations are those, they do not explain the physical principle why it is done, but if you use those empirical relations, you can understand, I mean, rather you can obtain the useful value of those parameters. So empirical relations are not very common in science study, because pure science, they always must go through a definite understanding equation relations. But in engineering, we sometimes rather take it to be granted that rather than understanding from the first principle, we have to go through the implementation using those relations, which is a correlation. Say the heat transfer coefficient h to the power zero point 0.2 is equal to the on right side there are 3 or 4 parameters which are also certain power. But why these power values are there? They are mostly determined from the experimental verifications and repeated experiments. So these are useful for the actual industrial applications. But obviously, initially you have to understand the physical principle too. This I'm discussing just because of to give you an idea. Never be with that very, I mean, rosy picture that you will go in a center and then you will start making design and the industry will vote for that. They have a standard design process, they have a standard empirical relations. But to make any development, the R&D section has to understand the entire physical process very clearly. Anyway, so now I'm going into the discussions of some of the pebbles we usually use in the market or rather in the actual industry. So the pebble air heaters are designed to heat air and other gases to higher temperatures, say even up to 1000 degrees Celsius. The pebble heaters is quite good for heating that to that temperature even. Then is economically feasible using the recuperative principle. Means for a waste gas, say at a temperature of 1500 degrees Celsius, if you want to use that up to a temperature of up to a certain recuperative heat exchanger process, then the temperature rise maybe say some of the order of some 500 degrees, 600 degrees Celsius. I mean, I'm just taking a number. I'm not telling that these are the sacrosanct. But even the pebble bed, if you can reach up to 1000 degrees Celsius temperature by of air heating, then it is significant heat regained. And obviously, the cost of pebble bed installations will be justified for through this particular temperature achievement. And then the spherical pebbles of 0.5 inch diameter of mullite compositions. The mullite is a very specific material consisting of aluminum oxide and the silicon oxide, and around 70%, 30% compositions of these two materials. And there is a definite reason of using this because I have only discussed about the heat capacity. But another important point, if you just observe there, you'll find out continuously solid pebbles are passing through in a solid flow mode. And in solid flow mode, there is a very serious problem. We called it attrition. Attrition means whenever two solid particles move continuously side by side or in contact with each other, always there will be some wear and tear. So these material must be to, as far as possible, resist those wear and tear, because in short time what will happen, they will generate some dust. Dust means these are not very easy to flow, so they will block the entire passage. So this mullite composition is pretty good strength to get that wear and tear situation. And the texture, outside textures of those pebbles are also sometimes has to be compromised, because if those are very much uneven, then they causes the possibility of more tear, wear and tear. But they improves the better heat transfer. So that's why this pebbles size, I mean, how much will be the diameter? Because think about the situation for a given volume. If you increase the diameter of the pebbles, then what will happen? Lesser number of pebbles will be there in a given volume, and then the passage passing in between those pebbles will be rather effectively larger passage will be there. So the air will pass through those larger passage in a shorter period rather than effectively increasing the heat transfer. But if you make those pebbles very small, like particles, then what will happen? Effectively, you cannot have any airflow at all. So making the pebble size is also optimized. I mean, some optimization problem. And in that case, around 0.5 inch diameter is considered to be, which becomes optimum, where the air can also flow and you can get a good contact between the solid pebbles and the air that is flowing through it. So the values and the compositions, whatever I have mentioned, the mullite composition has got acceptable specific heat and or heat capacity, and simultaneously it has got the strength to resist the wear and tear during the solid friction of during the solid friction during the solid flow of those pebbles. Application area. air or gas heating hydrogen or natural gas for the reduction of metallic oxides, then producing ethylene from a hydrocarbon feed source. In fact, the subsequent two applications are not very important. In general, you are aware that if you want to have significant temperature rise of gas, which is otherwise not possible through a conventional heat exchanger, then we use only pebble gas heaters. Any queries up to this? I'm not very sure how many devices I can cover because I have to around 16th or mid of this month you have the session closed, and I've already maybe there is one faculty council meeting and your class test mode will be decided there. Whatever maybe, if I get it from Dean, I've already informed him. He will inform me as early as possible as it is decided. But we can have the content at least. I will try to cover another one or two areas of energy conservation apart from the waste heat recovery. So I'm just discussing some of the possible devices for getting the idea, and these are not the exhaustive. There are many more devices of waste heat recovery, but I will just give some ideas of getting the example or test of the functional process, not even the design. That's not possible in this mixed class. In mechanical, we rather make certain partial design process also. So I am assuming that the pebble gas heaters are done. If you don't have any queries, this I will not discuss. This is recuperative burner. This needs certain, the idea of combustions and other things. So this I will skip. Economizer, should I discuss? No, let's leave it also because I will not be able to cover then other topics. Economizer also, waste heat of boilers also I leave. Okay, don't discuss these things. Thermal fluid heaters also let's skip. Then the next topic, this is not needed. This is one interesting topic. Fluid bed, let's discuss. Okay. So the next topic is the fluidized bed heat exchanger. So what is fluidized bed heat exchanger? I guess the chemical engineers know this, should know this term. Anyone from chemical engineering, have you heard about the fluidized bed? Have you heard about fluidized bed?
Yes, sir.
Fine, I guess so. But the others, I'm sure all have not heard about it. So maybe for chemical engineering students, it will be a little bit redundant, or rather you already know it, but I have to discuss for other students. Now, what is fluidized bed? You have to understand. Now, initially, let's try to understand what is fluidized. We have called it not fluid bed, but fluidized bed. Means this idea is, actually it was invented by, most probably his name is Fritz Winkler. If I just don't mistake that particular name, he's a German engineer. So the concept was, it's a brilliant invention, but through accident. What happened actually, say in a perforated plate with some small particles on it, if you allow some gas to flow through this perforated plate, that means the plate is so perforated that gas or air can pass through it smoothly, but no particles can drop through those porous perforations. So initially, depending on now what you are doing, you are increasing the airflow slowly. What will happen? But remember, these are not pebble-like things. These are particles. Means dimension that was of the order of some 0.5 inch. But here the dimensions is of the order of some few millimeters. That's the particle. Say sand particle. Mostly sand particles are used here, or sometimes the limestone particles are also used as a additive material. Let me explain the principle of fluidization at first. Then I will explain why the fluidization is. Fluidization is a very big area. It is not only used for heat transfer enhancement, but also it is used for reaction engineering, which is the basic important area of one of the very important area of chemical engineers and mechanical engineers also, for the process of gasification, combustion, etc. Anyway, so we are interested here only the heat transfer aspect of fluidization. But fluidization is a generalized principle which can be used for many applications, enhancing reaction, enhancing heat transfer, enhancing combustion. Combustion is also some sort of reaction. Gasification is another very important reaction through which you can get the gas produced from the solid fuels, synthetic combustion gas from the solid fuels. Anyway, Now, initially, as I was explaining, before I give the text, try to understand the basic physics of the fluidized bed, which the chemical engineers, for them it may be a repetition of the concept. So you have a small perforate. That means the perforations are so small that gas can pass through it, but the on that plate, on top of that plate, the particles cannot pass through the perforations. Now, initially the air is at a very low velocity. So what will happen? Those airs, just like pebbles you have initially, or rather previously exposed to, airs will try to pass through the interstitial spaces so that the particles will not move, but small amount of air, finding out the gap between those, even those small particles will pass through it, and no movement of those particles will happen. This situation is called fixed bed. Then, if you increase the air velocity, then slowly at a time, the particles will be on the verge of motion. This is called incipient fluidized bed. Why? Just try to understand. That's why I'm not giving the dictation. The same thing I'll give the dictation, but try to understand the situation at first. Then, if we increase the air velocity even more, then what will happen? The particles will start living and start movements. And movements means the particles will move up to certain height from from that plate, and then interestingly, when the air passes and those particles are carried up, what will happen? All particles will not move together. So obviously the density of those particles floating in the air will slowly decrease, and air will have more passage as the particles go up. In that process, what happens? The particles eventually comes down again, but the air or gas passes out. So this phenomenon means, if you look from top, it appears to be as if that solids are like a boiling liquid or fluid. And here, the behavior of that air and solid particle mixture has got a lot of similarity with a fluid. That's why it is called fluidized bed. And as looking from top, the fluidized bed appears to be a bubbling liquid. That's why this sort of fluidized bed is called bubbling fluidized bed. In fact, if you increase the air velocity, then those particles will be carried over more, and they may go out of the chamber. And there is a solid gas separation device, either cyclone or impact separators. There are different mechanisms, there are different devices where the solid will be collected at the bottom and gas goes out to the atmosphere free of the solids. Then these solids are recycled. So that's the zone of the circulating fluidized bed. And there are different definitions of fast fluidized beds, etc. So in short, as it's a mixed group, what I can just tell you, then I will give the text. If you increase the air velocity through given particle, some quantity of small particles, then initially there will be no movement of the particles for a lower gas velocity. Then with increased gas velocity, the solid particles will start moving, and then they will be confined up to certain velocity within the above the plate, and this zone is called the fluidized zone, or specifically bubbling fluidized zone. And then also try to see, why do you create this bubbling fluidized bed zone at all? Now think about our objective. This bubbling fluidized bed can be used for several purposes, and that's why fluidized bed is a general principle. But for the heat transfer, what is our issue is, if we can just put a heat transfer surface within this fluidized bed zone, then what will happen? On the heat transfer surface, you will have continuously solid particles impinging on the surface. And the solid particles, if they are heated, then obviously, if they have a high temperature, then effectively the heat transfer between this air solid mixture and the surface will be several times increased than the normal gas to surface heat exchange process. That means the fluidized bed heat exchange process is several times larger. I'll show the graph later on. The several times larger than the only air to surface heat exchange process. But there are certain problems also. Problems means one of the important problems you can understand from your common sense. Here, the solid particles are impinging on the surface. So the surface facing those impinging solids will have a fast erosion problem. That means the tube leakage is very, regular, or unless you take proper measures of the fluidized bed, because there the solids get in contact with those tubes. So sometimes we just give some ceramic coating at that point, and ceramic coating decreases the heat transfer, but simultaneously you have to save those tubes from erosions, etc. So now I give the formal text, and then the device descriptions, not necessarily I will give, but you can just understand, I will show you. Just write down the basic principle of fluidized bed at first. So in the text part, just write down, if air or a gas, if air or a gas is passed through, is passed through solid particles on a perforated plate, solid particles on a perforated plate, comma, then initially, at low gas velocity, at low gas velocity, there may be, there may be no movement of the solid particles. And the gas only passes, and the gas only passes through the passage within the solid, through the passage within the solid particles. Full stop. The bed of solid particles, the bed of solid particles is then called fixed bed, within quote, fixed ed, fixed bed. Full stop. With even higher velocity, with even higher velocity, particle starts moving up, particle starts moving up, and the specific condition, and the specific condition when particles are on the verge of movement, on the verge of VRG, verge of movement, the bed is called incipient, INCEPIENT, incipient fluidized bed. Full stop. If the air velocity is further increased, solid particles will start moving up, but may come down again, from certain height. Then the corresponding zone with gas solid mixture is called bubbling fluidized bed. As looking from top, the surface appears to be air bubbles continuously bursting out, bursting out at the top surface. Full stop. Any any heat exchanging surface within the bubbling fluidized bed may achieve significant enhancement of heat transfer as gas solid mixture passes over the heat exchanging surface. However, this may cause severe erosion, EROSION, as solid particles impinge, imping, on the heat exchange surface. Hence, designing fluidized bed heat exchange with optimized heat transfer, with optimized heat transfer and surface erosion has to be decided based on experience. In fact, I had some recently interactions with the DVC people. Uh, they had certain fluidized bed combustion process, the power generation, and they have experienced several problems are coming up. So, though we teach, and fluidized bed is also established in many places as a good options for combustion process in the boilers and etc. etc. There are certain easy pollution control options also. Maybe the chemical engineers know those things a little bit, but the maintaining the steady bed in a fluidized bed operation is also a very good industrial challenge. And in fact, the people who are, I mean, expert in maintaining the steady fluidized bed, they are also given very high value in the industry. Anyway, so, but I'm just, as a teacher of academic institutions, I'm supposed to mention these principles only, not actually the all problems I can discuss in this class. So you have understood that the basic thing is what is fluidized bed, number one. Number two is up to bubbling fluidized bed is our discussion area, though circulating fluidized bed and fast bed, these are also application areas, but I'm not going into those zones. In bubbling fluidized bed, there are two important issues. One is the heat transfer characteristics improves because rather than only gas solid mixtures passes over the heat exchanging surface. But as the heat transfer surface increases, there is simultaneously significant erosion problem. So optimization between the erosion and the heat transfer coefficient is a operational experience decision. And in fact, in fluidized bed, I still know many companies who operate, they have got their own database to deciding at what air velocity they will operate their fluidized bed to maintaining steady, stable bed and simultaneously having optimized erosions, etc. But now I'm coming to not the entire broad area of the fluidization, but only the fluidization heat transfer characteristics for the waste heat recovery. Now, see the structure. I'm not going to describe it in text. You have these two valves. I mean, there should be one more valve actually. Here, one valve. One valve is also good enough. If you just simply put it into the horizontal mode, then what will happen? This passage will be blocked. So when you want to operate this fluidized bed heat exchange process, this valve should be completely in the horizontal position so that this cross-sectional this duct will be blocked for the air passage through these directions, though it has been shown by arrow. When it's in partially opened or full opened in the vertical condition, then entire gas will pass through this, bypassing this fluidized bed. But if it passes through the fluidized bed, then you have got the distributor plate. Distributor plate is that plate which is basically the allows the gas to pass through this plate, but the solid particles, what is put on this distributor plate, starts moving, creating that shallow fluidized bed or bubbling fluidized bed. The shallow means if you make a slow, I mean very small velocity, then the expansion of the bed will also be confined within a very shallow zone so that the effective depth of the fluidized bed will be less. But if you increase the velocity, obviously this zone will increase more. That means it will be expanded with the up to certain height. Then finally, if you go on increasing, it will go out. The particles, sorry, the particles may go out. But that's the fast fluidized bed zone. I'm not going into that part. So now see the situation. So you have the heat exchange surface, extended surface heat exchangers here inside. Then heat exchange process happens. Now I'm coming to the next part as the basic principle. What should be the fluidized bed velocity? Now, one particular term, I will define it here in the next paragraph. Let's see. You have the terminology U suffix sup in the x-axis. That means superficial velocity. What is this term? The superficial velocity is velocity which is superficial. Why it is called? You see, whenever there is a fluidized bed, then it's a mixture of solid and gas. Moreover, you cannot determine with 100% assurance how much is the particle density because it is continuously changing. Particles are going up, coming down. It's called basically core annulus model in fluidized bed, which is the standard practice we do, where the central portion is mostly air dominated. That means smaller number of particles, but the zone closer to the wall is having more particles. Anyway, so there is not even uniform particle density in the fluidized bed too. So if you want to determine what is the velocity of the air solid mixture, it's very difficult to define. So what is done actually, the air velocity, that is very easy to measure because before it enters into the fluidized bed, if you have a air flow rate measurement, then you can say, and depending on that flow rate and knowing the cross-sectional area of the fluidized bed, say you know the air flow rate, this much meter cube per second. If you have the cross-sectional area of the fluidized bed, then divided by that, that flow rate divided by the cross-sectional area will give you the velocity of air. But this velocity of air, honestly speaking, is not the true velocity of air. Why? Because the entire fluidized bed is not filled up with only air. It is filled up with air and solid mixture. So this definition of this air velocity, if we accept as a fluidized bed particular air mixture velocity, then it is not proper, and that is not uniform also throughout the fluidized bed. That's why this definition is a superficial definition of velocity. But in all fluidized bed calculation, we have to do it on the basis of this superficial velocity only, at least in industrial practice. There are certain laser-based technique to measure the particle density at different locations, but those are sophisticated research. I am not going to that part. So just write down. This has to be introduced. Rather, I think as to save the time, let me explain this graph and then together I will give the text together, defining superficial velocity and this explaining this graph. Now, what is this graph tells? There's different zones of fluidization. As I have mentioned that if you increase the superficial velocity, means air velocity passing through the fluidized bed, then initially up to certain value of the superficial velocity, which is U suffix mf. Mf means minimum fluidization. Up to this velocity, you have only no movement of the particles. Only the air movement is there. So that's why that particular time, this bed is called packed bed or fixed bed. Same terminology. You can call it packed bed or fixed bed. Then the fluidization starts, and when the fluidization starts means solid particle starts moving. That means up to blue line, there is a linear change of the heat transfer coefficient increase with respect to air velocity. But after that, the rate of increase has got a non-linear characteristics when the solid particles start moving and the fluid bed is created, not packed bed. This red line is for the movement of the solid particles or the fluid bed is created. Now, you see, that this increases the heat transfer characteristic, the heat transfer coefficient increases up to certain velocity, which we have defined as UOPT, means optimum. Optimum, why? Because at that superficial velocity, we have got maximum heat transfer coefficient. Then it decreases again. And then this zone is called fast bed or pneumatic transport zone. In between, there is a fluidized bed. Why? Before giving the text, I'm trying to make you understand that fixed bed or packed bed definition is particles have no motion, but there is air velocity through it. Then at minimum fluidization velocity, we have a fluidized bed created because there is a zone in which air solid together moves. Then with air velocity, we are having more heat transfer coefficient. What is the reason? Reason is we have higher Reynolds number, or the so-called heat transfer coefficient increases with velocity of air solid mixture. But above certain velocity, why it decreases? In that case, you can understand that above certain velocity, the particle density within the air will decrease. Means then you are as if losing the heat transfer coefficient, because sufficient particles are not there, and effectively it is tending back again towards gas heat exchange rather than fluidized bed heat exchange. So that zone is called fast bed and or the pneumatic transport zone. So you have to decide what should be the optimum superficial velocity for getting maximum heat transfer coefficient. So deciding this point corresponding to the maximum heat transfer coefficient is the essence of deciding the operating point of a fluidized bed heat transfer. Anyway, do you have any queries, or I can just give the text part dictation? Just write down, as the velocity of air and solid particles, as the velocity of air and solid particles, velocities of air and solid particles is difficult to determine separately, in a fluidized bed, comma, superficial velocity is defined which is corresponding to only gas velocity though actually gas solid mixture move together. Okay, so you have understood what is superficial velocity, because the definition of superficial velocity is though there is a gas solid mixture moving together, but you are defining that particular on the basis of as if only gas is flowing, no solid is there. That's why it is called superficial. That means it's not real, but that's the standard practice of defining the fluidized bed gas velocity, though it's a gas air mixture. Now just write down this explanation of the optimum point. So just next sentence is, during packed bed, you know the meaning of packed bed. During packed bed operation, heat transfer coefficient increases linearly with superficial velocity. Full stop. However, during fluidized bed operation, increase of heat transfer coefficient is faster, FAST faster than the packed bed in a non-linear mode. Next sentence, heat transfer coefficient achieves a maximum value corresponding to a maximum value within bracket. You can write down H max just to identify which point. A maximum value within bracket H max corresponding to an optimum superficial velocity within bracket U suffix OPT, that means optimum. And a higher velocity than U OPT, a higher velocity than U suffix OPT, that means optimum superficial velocity, will decrease the heat transfer coefficient as particle density in air decreases in that fast bed zone, which is actually used for pneumatic transport. And for your understanding, the pneumatic transport is any transport process of particle using the air flow or gas flow. So this zone is better used for, carrying of particles using the gas flow or air flow. That's called the pneumatic transport. So this zone is not suitable for higher heat transfer coefficient, but more suitable for the pneumatic transport. So initially, from the packed bed to the fluidized bed, up to the optimum velocity, you have a continuous increase in a non-linear or faster way. But then achieving the maximum heat transfer coefficient at the corresponding to the optimum superficial velocity, further the heat transfer coefficient decreases. That's the fast bed zone or pneumatic transport zone. So we need to operate specifically within this, between the UMF, at the minimum fluidization velocity, and the U optimum, closer as far as possible to the optimum superficial velocity, when you can have the corresponding maximum heat transfer coefficient. Any queries up to this? No queries. So I can go to the next slide. Advantages of fluidized bed waste heat recovery. Heat transfer is increased 3 to 5 times. No doubt it's a good advantage. So you can enhance simply by employing the fluidized bed, significantly higher heat transfer coefficient. Then bed material action keeps the fin tubes clean. This happens because if the waste gas is full of dust, then also it doesn't get deposited on the heat transfer surface, because the particle inherently present in the fluidized bed will clean those dust continuously. So surface cleaning, outside surface cleaning is not required in fluidized bed, but in other processes where only dirty gases passes over it, you need to clean the outside surface very regularly. Then the bed temperature is uniform. This is also another very good quality, because the temperature, as there is a solid loading in the gas, the temperature becomes almost uniform by this, mixture of this air solid mixture. Then the pressure drop is low since the bed is shallow. In fact, the airflow through these solid particles, there is a pressure drop of the air too. But if the bed depth is low, then automatically the pressure drop will also be very low. So generally in heat transfer purpose, this bed is specifically maintained at a shallow depth, not having that bed expanded. But in reaction process, it's not basically the same operating zone of the heat transfer zone, because those who are chemical engineering students, they might be knowing that you need to control the bed height depending on different types of reactions, because reaction in shallow bed is not very effective, because in that case your the conversion of the amount of those reaction process will be comparatively lower. So there the optimization principle of the bed height is a little bit different from the corresponding heat transfer optimization process. Okay, so then I'm not going to the further discussions today. The time is over. I'm not yet decided whether I will go for any more device discussion. Maybe I can switch over to the waste heat recovery economics. Then maybe I will switch over to other modes of energy conservation, the technological aspects. Any queries up to this? Balan.
Sir, in the last class, you have discussed about runaround coil, but I have not understood the working properly of that thing.
I cannot solve it. I'm sorry. You have to take the notes from your friends. Because if
Yes,
you cannot
I have
just
taken the note.
Ah, but only suggestion I can give, if you can, students can arrange together of get things clarified in a physical mode, because it is not the COVID situation, but the open elective class is forced to be in the online mode just because of taking the involve the students of different departments. But if you wish to have some physical, exchange class, sometimes you can arrange it, and I can be physically present to clarify as much as possible. But if somebody cannot, I cannot reach to somebody due to the, technology problem of the poor connections and other thing, I cannot solve it. I'm also helpless. So only thing I can do, if you want a physical class, I can arrange for that. No problem. Any other queries? If not, then I'm going for the roll call. Sheikh Mohammad Ali? No. Then Nityendu Gupta?
Present, sir.
Okay, fine. Then Shaunak Agarwala? No. Anubhav Shah?
Present, sir.
Anubhav present. Okay, fine. Good.